In section 1.1, one of the main ideas of the section is the figure that you're seeing here on the left. This is the figure which shows the relationship between the secant lines and the idea of a tangent line. Okay, one of the things that we reviewed in class was this very important formula, the slope of the line. We reviewed the slope of the secant line between the points C, f of C, we'll call that point P, and another point Q called X, f of X. Okay, and so we called the secant, the slope formula we remembered was the change in the y over the change in x, and the change in the y values is f of x minus f of c divided by the change in x, which is x minus c. And you'll recall that very importantly that in our book in this section, c is a specific value, a value of x, and the book is using here x to be any other value of x. Okay, so what we're seeing here, we did this graph moving in class that we had the point P, we have a point Q, and this line right here, that was the secant line. And if you adjust the values of x so that x gets closer and closer to the specific value of c here, that the secant lines are going to keep changing, and those secant lines get closer and closer to the tangent line. And so that's what we want to do a quick example of with the math and the symbology right now. So for example, let's say that our specific function given is f of x is equal to x squared, and our specific value of c, let's call that equal to 2, right? And so if we're going to find the slope of the secant line, slope between 2 points on this function x squared, with one of the points being 2 f of 2, right? 2 is our c value, f of 2 is our f of c value. Between this point and x comma f of x, where that point is x comma the y value x squared, so the slope between those points is going to be x squared minus the function evaluated at 2 is 4 over x minus 2. Okay, so there is our slope formula. And if we try to, maybe create some specific values, so for example, what if x was equal to 3, right? Then we'd have the slope between the function, the value of the function at 3 minus the function at our point 2, 3 minus 2, in which case the slope of the secant line would be 9 minus 4 over 1, which would be equal to 5. Okay, so, and then if x was equal to 2.5, for example, so we're going from 3 and getting closer to 2, so 2.5 is closer to 2 than 3 is, we would do the slope of the secant line would be the function at 2.5 minus the function at 2 over 2.5 minus 2. That's probably a calculator problem, so I'm going to do that real quick over here on the left of Desmos. Let's say that your function is f of x is equal to x squared, and we want to compute the slope of the secant line between the x value of 2.5 and the x value of 2. So we need to find the change in the y values, and then we will divide that by 2.5 minus 2. So we can see here that we get a slope of 4.5, right? One can easily get those answers just by plugging into the slope formula. Notice that this formula right here is the slope of the secant line between the point P to f of 2 and any other value of x. So for example, if you put 3 into this function here, the slope formula evaluated at x is equal to 3, you would get 3 squared minus 4 over 3 minus 2, which is 9 minus 4, which is 5. So if you have a slope of the secant line formula, you can put in any value of x that you want to get the slope of the secant line between those 2 points. So we're pretty comfortable with the secant line formula right here, the secant line function, and doing some various secant line slopes here. So let's take a look at Desmos, maybe take a look at what we have just done with that green formula here. So notice that we can create two f of 2. There is a point that we can see on the x squared function. So that's our specific value and the specific point P on the function. And then we can create x comma f of x. I'm going to use big X here because Desmos won't let me use little x again. So here I'm going to do in the picture what on Desmos what the picture in our book is doing. I'm going to take the values of x here, the 3 dots along the bottom, getting closer and closer to 2. So let's add a slider bar for x, and let's adjust the values. X goes from, let's say, 2 to 3. And then let's make the Desmos include a variety of values, right, that differ by 0.1. So here is the value of 3, another point Q at, and maybe we should add a label for that one, 3, 9. Okay, now let's conclude in this picture the slope of the secant function, which is big X squared minus 4. This is the formula that we showed in green over here. This is our slope of our secant line function divided by x minus 2. Okay, and I'm going to call this, give this a name, I'm going to call this m for slope, and it's a function of x, where x is the value of the point. Okay. Let's see, did that not? All right, I guess that is not, maybe Desmos is not, there we go. Let's just do this then. There we go. I won't have to give it a name. So notice that as the x value changes, when x is 3, our slope of our secant line formula comes out to be 5, which is what we showed before. And as the x gets closer, let's go to 2.5, we should see our slope formula be 4.5. Okay, so what we're technically doing is making secant lines between these 2 points, okay, and we are making them get closer. The slope of the secant line should get closer to this tangent line. So I'm going to pause the video for just a moment so that I can include in Desmos the slopes of the secant lines and the tangent lines. So this will just take a second. I just took a moment to add these lines 7 and 8 to our Desmos. Just didn't want to take your time with that while I showed that. The blue line here, the blue dotted line, you can see that that is the slope of that is the secant line between our 2 points. Here's the point P in blue and our point Q in green. And that secant line changes depending on the 2 points. You can see here is the blue line is going to change as the x value, the green dot gets closer and closer to the point. And the slope of the secant line keeps changing. And the question is, what happens as the value of x, as you get closer and closer to the point of interest there, the point that we have specified at 2, 4. So you can see that the secant line is changing, not a lot, but it is changing a bit. And the closer we get right? What we're getting, that those secant lines are getting close to is this last line here. I've got a shortcut for the equation of the tangent line. Okay, so we can see here, we'll do this in slow-mo. Red is the tangent line. It's this line that just matches up with the function at that point and is kind of angled the same. I'll say more about tangent lines in a bit, but there's our tangent line. And the secant line, as the 2 points get closer and closer, right, the blue line, dotted line, should get closer and closer to the tangent line. And the slope, we can see here, is getting closer and closer. Looks like we might be getting closer and closer to the number 4. So we'll see we'll see that more as we progress with the course. Now what's interesting is that if you were to choose a different specific value of x, like changing your c value here, right? So maybe we choose our c value to 0.7, right? The same process still applies that, right? You can see here that the secant lines are now more pronounced. You can see that the secant line between those 2 points kind of cuts off the curve. But as we get closer and closer and closer and closer, we can see that the secant line is, and we need to get close to our c value here, right? That as we get closer and closer to our 0.7 value again, the secant lines are getting closer to this thing called the tangent line, right? And the question that we need to address in the next class is, what does the slope of the secant line, what do these numbers 2.7 get closer and closer to? Okay, so I should technically, if I want to do this for any value of c, I should call this c squared, and then I should put the value of c here, so that as the c value changes, so too will the slopes of the secant lines. All right. So I just want to focus on this tangent line for a second and just kind of remind everybody kind of what it is what our goal is. Okay, our goal is to come up with this thing called the tangent line, the slope of it and the equation of it. And what we're seeing here is that this secant line, the tangent line here, is this, as you move this dot around, that this red curve is the tangent line. It is the one that if you were to zoom in on this function, it's the line that goes through the specific value of c, and this tangent line matches really well with the function at that point, right? So it's kind of an approximation of the function. So if you move to a different location on the curve, like right over here, and you were to zoom in, that red curve is really good. It matches really well with the function at that point, specific point that we have chosen. All right, so that's just a quick video on the goal and the relationship of the tangent lines and the secant lines.